Hello friends, I welcome you all to this session on power plant engineering. So in this lecture, I'll tell you that how to understand the thermodynamics of closed feed water heater. So here you can see that two closed feed water heaters we are having. The steam is extracted, one from higher pressure side, another one from lower pressure side, and the water is coming. So there is no direct contact between the water, feed water, and the steam. Steam condenses, releases its latent heat of condensation and gives to water. Water gain it and then moves out with a higher temperature. Whereas the condensed steam using this drip is transferred to the next heater. And the last one, there can be several, but the last one is dumped into the condenser. So now if you look, M1, M2 is coming extracted from the steam in the turbine itself. So the amount will be 1 minus M1 minus M2 if 1 kg of steam is entering into the turbine. Then here if you look, this M1 is transferred to the lower feed water heater and M2 is also already there. So the mass which is going out will be M1 plus M2. And this M1 plus M2 is dumped into the condenser, which is receiving a mass of 1 minus M1 minus M2. So the mass, this plus this, will be going out. So here, after the condenser, we will be having 1 kilogram of water. So this is basically the mass conservation. So let us do what? Let us try to draw the TS diagram for this cycle. So let's say this is the higher pressure, and now the first one is point number 1. So point number 1 is this, and from the total expansion is from 1 to 4. So let's say this is the 4. I am showing only the ideal expansion. Then from between 1 to 4 there are two extraction point 2 and 3. Let's say the first point is here 2, the second point is here 3. Though they will be depending on the problem, but still let's say they are here, doesn't matter. So now what is happening? The steam is extracted, M1 kg is extracted at point 2 and M2 kg is extracted here. Now if you look, after extraction, the condensation is the point number 5 and then the pump is point number 6. Now feed water from 6 to 8 is having the same pressure. Okay, so now the task is to locate where these points 6, 7 and 8 are. So if you look closely, that steam after extraction from point number 3 is condensed and the state is 10. So this state will be 10. Okay, so this is indirect contact, so there will always be a terminal temperature difference. That means the exit feed water should always be lower than the entry point or the extracted steam temperature. So there will be a temperature difference. So let us say that the exit, it is 7 here. So 7 should be slightly below than this point number 10. Why? Because this is indirect contact. So there will be resistances in the material itself, so that the energy transfer is not taking 100%. So 100% energy transfer from steam to water will not be there. Likewise, if you look point number 8, so extraction is happening at point number 2. So this is the point and this is point number 8. So point number 8 and point 2 is coming, it is exiting point 9. So this is your point 9. Okay, and then if you look, the exit feed water heater is having state 8, which should be slightly lower than point 9. So let's say this is point number 8. Okay, now here 1 kilogram is coming. 1 kilogram is, let me change the pen. So this is 1 kilogram. Okay, so M1 kg we have taken here. So here the expansion will be of 1 minus M1 kg. So M2 is also coming out. So here the expansion is of 1 minus M1 minus M2. Now if you look, At point number 9, so this fluid is transferred to the feed water heater, lower feed water heater. Let's say it is feed water heater 2 and this is feed water heater number 1. So this M1 is transferred to the feed water heater 2. So this is irreversible mixing, so that's why we are showing it like this. Now, and here after 10 both M1 and M2 are fed into the condenser. So this is the one. Okay, so that's it. So this is your Rankine cycle for the case where only indirect contact feed water heaters are there. Now the question is how to write the uh, heat transfers, work interactions and so on. So let us do one by one. So let us come to the turbine first. So here if you look, turbine, so this is the first stage work output with 1 kilogram of steam expansion. So it is 1 times H1 minus H2. Then here the amount of steam extracted expanding is 1 minus M1. So it is 1 minus M1 times H2 minus H3. Then here the expansion is of 1 minus M1 minus M2. So what is the mass? This is the mass and enthalpy drop is H3 minus H4. So this is the total work output from the turbine. Whereas the work input in the pump. So now if you look here, this is 1 minus M1 minus M2. The mass which is going is M1 plus M2 from here, adding, and then you are getting what? 1 kg here. So inside the pump is handling 1 kg only. So here what we can say is it is 1 times H6 minus H5. So this is the work we have to transfer to the pump. Now comes the condenser part, that is the heat rejection, or let's say first we will be solving for heat addition, let's say Q1. So what is Q1? Q1 is the amount of heat added in boiler. So it is entering at 8, exiting at 1, and this is your Q1, handling 1 kilogram only. So it is 1 times H1 minus H8. So it is 1 times H1 minus H8. Now what is the heat exiting from condenser? This has to be done. So if you understand this closely, so this is your condenser, you can draw the control volume. Okay, so let us do what? Let us draw it here. So this is your condenser. So here the 1 minus M1 minus M2 amount of steam is entering at point number 4. Very good. And it is exiting at point number 5 with a mass of 1 kilogram. Here M1 plus M2 mass is coming from the lower feed water heater, that is 2, and from it this the state is 10. So this is the one. So here we have to write the energy balance for this, and at the same time this is doing what? This is releasing heat into the atmosphere Q2. So we know that from the steady flow energy equation, energy entering plus the heat transfer, energy exiting plus the shaft work. This is SFE, steady flow energy equation. There is no shaft work involved, neglecting kinetic and potential energy terms. So what we will be getting? Whatever entering. So inlet is at 4 and 10. So it is 1 minus M1 minus M2, and then this is point number 4, that is H4, and then it is also entering. So this is plus M1 plus M2. Okay, and this is 10, so it is H10, and the heat which is here lost, so it is minus Q2. I am just taking the magnitude. So the sign is telling you that the heat has been lost from the condenser, and then the exit is at point number 1 with 1 kg. So it is point number 5, sorry, with 1 kg. That is the one. So if you want to find out what is Q2, you can simply say Q2 will be 1 minus M1 minus M2 H4 plus M1 plus M2 H10 and then minus H5. This is the heat loss. Okay, done. So turbine work, pump work, heat added in the boiler, that is this Q1, and the heat rejected from the condenser, that is Q2, all we have evaluated. So now the question comes, is it all? No, because you cannot solve this expression numerically once until unless you know the values of M1 and M2. So for that, what you have to do is you have to do the control volume analysis for heaters. So what we'll do is we'll snip this portion and we will bring this here for our understanding. Okay, now let us do what? Let us do the analysis for feed water heater number 1, this one. So for feed water heater number 1, we will be getting what? We will be getting M1. So again, the same equation, that is energy entering plus heat interaction, energy exiting with mass, and then the shaft work. What I am assuming, it is only a mixer heat exchanger, so no shaft work. Also, we are assuming that the heat addition is happening adiabatic and neglecting kinetic and potential energies. So what is entering? M1 is entering from 2. So it is M1H2, very good, plus this is also entering at 7. So what is the mass? 1 kg. So it is 1 into H7. Okay, then what is exiting? This is exiting. So this is 1 kg only, it is H8. And this is also exiting. So it is M1. It is M1. So M1 times H9. So what is required? M1 was expected. So we can write M1 and that will be equal to H8 minus H7 divided by H2 minus H9. So this will go there, H2 minus H1, and this is okay, that's it. So from here you can evaluate what is M1. Once M1 is known, then what we can do is we can jump to M2. So that will be evaluated from feed water heater number 2. So if you look here, again the same thing, entry total energy entering with mass should be equal to total energy exiting with mass. So what is entering? M2 is entering at H3 plus this is also entering. So what is the mass at point number 6? So if you look, this is 1 kg, so it is 1 kg only. So this is 1 kg and 1 into H6. Okay, so this is entering, this is entering. Also this is entering. M1 is also entering at H9. Okay, so this enters, this enters, this enters, and the amount which is leaving is this one, M1 plus M2, and this 1 kilogram at 7. So what is the state M1 plus M2? So this is nothing but state number 10. Okay, so this is state number 10. So what we can write here is, it is M1 plus M2 state number 10, that is H10 plus 1 H7. Okay, what is required? M2 is required. So I can write this thing as M2 H3 minus H10, and remaining we will keep there itself. That is M1, and this is H10, this will go there. So it is H9 plus H7 is there and minus H6. So M2 will then be equal to M1 H10 minus H9 plus H7 minus H6 whole divided by H3 minus H10. So now previously you have evaluated M1. So with the help of this value of M1, you can evaluate what is M2. Once M1 and M2 are known, then what you can do is you can transfer the values of M1 and M2 in these expressions and evaluate the work output, turbine work output, pump work input, heat Q1 as well as this Q2, and then evaluate the efficiency of the plant. That's it. So here, one thing which you should understand is how to evaluate the differences in the temperature of feed water and steam. So there are so many cases. So we will discuss what? We will discuss these cases for our benefit. So point number 3 first we will take 310. This is the one. So here the bleeding is happening slightly below saturation or very close to saturation. So this is the case. So if I draw what, if I try to find out, this is your feed water heater, let's say, then this is the entry point of steam, and here the condensate is moving out. From here the feed water enters and feed water leaves. So this is feed water entry and this is feed water exit. So if you try to draw it, so this is the length of feed water, let's say, and this is the temperature rise. So what is happening if I change the color? Okay, the feed water is entering at point number 3 and exiting at 10. So this is your 3 and this is your 10, because during phase change there is no change in temperature. But what is happening to water? Its temperature is continuously rising. So this is what is happening. So if you look here, what is this point? This, because of this, there is a rise in the temperature of feed water from 6 to 7. Look here, from 6 to 7. So this, it can be your point number 6, this can be your point number 7. And now if you look that there is a difference, this difference, and that is what is called as terminal temperature difference. How we define it? It is basically the saturation temperature of bleeded steam minus the exit temperature of feed water. So in this case it will be H3 minus H7. So you can see that it is a positive, and it has to be, isn't it? Now, will it always be positive? No, we can't say this, because if the extraction point is above the critical point, or not critical point, sorry, saturation point, then this is the temperature. So for that, what is required? Desuperheaters are required, and sometimes drain coolers are also required if the temperature is going to be below that saturation. So let us see one general case here. This is the general case. This is your condenser, basically, not that condenser, this is feed water heater basically, and it is having desuperheater as well as drain cooler, let's say. So so what is happening? Steam is entering here. This is the entry point of steam, and from here the feed water, the condensed steam goes out, and this is the entry of feed water, and this is the exit of feed water at the higher temperature. So if we try to draw this, so this is the length, and this is the temperature. So let's say now the steam is entering, and then, and let's say this is what is happening. So why this is happening? Because if I take this condition here, it is from the superheated state, so that's why this is the one. And let's say it is also having some condensation there, or below that saturated liquid line, it has to move because of the lower temperature of water. Then what can happen? So let's say this is the water. So this is the entry temperature of feed water, this is the exit temperature of feed water here. Now if you look this particular case, so this part is basically for desuperheater, this is basically the condensation, and this is for drain cooler. Now here if you look the situation, this, the saturation temperature of bleeded steam is slightly lower than that of the exit feed water heater. In that particular case, the terminal temperature difference TTD will be negative. So you should remember this. So it is not always necessary that terminal temperature difference will always be positive only. It can be negative depending on the position from where the extraction has been taken. And that is the reason, because of this terminal temperature difference presence, means the difference in the exit water temperature and the saturation temperature, the total energy which you were expecting that the water should be taking away from the steam will not be taken, and hence they are slightly less efficient in comparison to direct contact. But the benefit when it comes to this in comparison to direct contact is that in direct contact feed water heaters, which are also called as deaerators, we have to use one extra pump, and that costs a lot. Whereas in case of indirect contact, though we are not getting that amount of energy, but still we are not using that pump. because the line pressure is not changing. So this is basically the benefit. Okay, so in this lecture, till this point only. In the next lecture, what we'll do, we will try to model one uh, indirect contact feed water heater in Excel, and then we will try to learn about the optimum degree of regeneration. So in this lecture, till this point only, thank you very much for watching it.